Hello, my name is Kakimoto. I'm a graduate student in agricultural economics at the University of Nebraska Lincoln. Today, I'll be talking about a new machine learning method for site-specific input recommendation. The application of machine learning method for site-specific economically optimal input rates called EOIR have been getting more attention in recent years. For example, Barbosa 2020 applied convolutional neural network methods and Krauss 2020 used random forest-based approaches. The conventional machine learning methods focus on the accuracy of yield prediction, and the past studies rely on the model's predictive power of yield for variety of their models. However, EOIR recommendations should be based on the causal identification of input on yield rather than yield prediction. Having good yield prediction capability does not necessarily mean that it is also capable of estimating EOIR well, because they are two distinct objectives. The lack of causal interpretation from existing popular machine learning methods has been increasingly recognized in many scientific fields, and this has led an emerging branch of machine learning methods called causal machine learning. Causal machine learning methods focus on identifying causal impacts of an event. In this study, we use causal forest, which was developed for estimating heterogeneous causal impacts of a treatment based on observed characteristics. Through our study, we proposed two causal forest-based methods, and we named them CF stepwise and CF-based. Using those methods, we addressed the following two research questions. The first question is that in terms of estimating EOIR, how do causal forest-based methods compare to other prediction-oriented machine learning methods? The second question is whether the predictability of yield is a good indicator of the performance of EOIR estimation. To address those questions, we conducted 1,000 runs of Monte Carlo simulations under 4 different production scenarios and compared the performance in estimating economically optimal nitrogen rates of causal forest-based methods to other methods. For prediction-oriented machine learning methods, we investigated their yield prediction performances in contrast with their EONR estimation performances. We use R-squared as an evaluation metric. Table 1 shows the mean R-squared of the estimated EONR for each machine learning method and modeling scenario over the 1,000 simulations. CF-based shows the best accuracy. Meanwhile, the performance of CF stepwise did not change as much as other machine learning methods. Part of the reason why is because the predicted treatment effects from CF stepwise are more susceptible to prediction errors than CF-based. To examine the consistency between yield prediction performance and EONR estimation performance of a machine learning method, we counted the number of simulation runs where a single machine learning method consistently shows the highest R-squared in both yield prediction and EONR estimation. Table 2 shows the result. For example, in model 1, random forest attained the highest R-squared for yield prediction 363 times, and out of those simulation rounds, random forest attained the highest R-squared for EONR estimation 57 times. If the model with the highest yield predictive performance is likely to result in the highest EONR estimation performances as well, the two numbers should be close. However, overall, there is no such a consistent relationship between these numbers. In conclusion, through this study, we found that our proposed CF-based method is capable of estimating site-specific EONR more accurately than other prediction-oriented machine learning methods, and the ability of predicting yield does not necessarily translate to good performance in estimating EONR. Thank you for your time.